Hello, Dan here from howtomechatronics.com, and in this video I will show you how I built a replica of the Mars Perseverance rover. Of course, inspired by the real rover, which is currently exploring Mars, I designed this rover in a way that everyone who loves this technology, students, makers, mechatronics or robotics enthusiasts and so on, can easily follow the instructions in this video and build their own Mars rover. Let's take a look at the main features of this rover. It employs a Rocker-Bogie suspension which allows the rover to run smoothly on uneven terrain and climb obstacles such as rocks that are up to twice the wheel's diameter in size, while keeping all 6 wheels in contact with the ground all the time. Each wheel has independent DC motor which drives the rover forward or backward. The 4 corner wheels have individual steering servo motors. In order to efficiently steer the rover and avoid tire slipping when driving around a curve, we are implementing the Ackermann steering geometry. With this geometry, we can calculate the speed and angle of each wheel depending on the turning radius. This means that when turning, the inner steering wheels will have greater angle compared to the outer wheels. At the same time, the inner wheels will have slower speeds compared to the outer wheels. For controlling the rover, I am using a cheap commercial RC transmitter which sends commands to the rover. At the rover, I have a suitable RC receiver which receives the commands and sends them to an Arduino board. Yes, the brain of this Mars rover is actually an Arduino Mega board, and for easily connecting everything together, I made a custom PCB which can be simply attached on top of the Arduino Mega board. The rover also features an FPV camera located in the camera's unit. It is controlled using a stepper and a servo motor, and I am receiving the real-time video on a smartphone. I would like to note here that many of the parts are actually not functional, or they are present just to match the appearance of the real rover. Also, the robotic arm is missing, but I plan to make the arm and add more functions to this rover in future videos. Nevertheless, now let me walk you through the process of building it, starting from designing the rover, connecting the electronics components and programming the Arduino board. I designed this Mars rover using 3D Experience SolidWorks, which are actually the sponsor of this video. 3D Experience SolidWorks is a version of SolidWorks with cloud capabilities which we get through the 3D Experience platform. Here everything works through the cloud, so you or anyone from your team can have access to the data or the models at any time from anywhere in the world. The 3D Experience platform also includes many useful productivity and data management apps. For example, the project planning app is a great way to organize your tasks, set deadlines and keep track of your progress. With the 3D Markup app, you can view, explore and take notes of the models from any device like a notebook, tablet or even a smartphone. There's also a separate cloud-based 3D modeler called SolidWorks X Design that runs inside your browser. It can be used in conjunction with SolidWorks or on its own, and it's great for modeling anywhere, anytime and on any device. Nevertheless, probably the most exciting news for many of you guys here is that starting from second half of this year, there will be a maker version of 3D Experience SolidWorks, which you can get for only $99 per year. So make sure you check out the links in the description and sign up to get notified when it will be available. Big thanks to SolidWorks for sponsoring educational content like this. Okay, so let's get back to the model now and explain how I designed this rover. My goal was to make this rover look as close as possible to the real Mars Perseverance rover. On the official NASA website, there is a 3D model of the Mars Perseverance rover, so I downloaded it and opened it in Blender. I took 3 pictures of the front, top and side view of the rover and imported them in SolidWorks. I wanted the size of the wheels to be 130 mm in diameter, so I scaled the pictures according to this dimension. Then from here I took all key dimensions like the width, length, height, distance between wheels, dimensions for the Rocker-Bogie suspension and so on. Now, according to these dimensions and the DC motors and the servos that I plan to use, I designed the rover parts in a way that they can be easily 3D printed and assembled, while trying to keep the appearance as close as possible to the original. For the Rocker-Bogie suspension I am using 20mm round aluminum profiles, whereas for the base frame I am using 20mm T-slot aluminum profiles. In order to assemble the rover we need various bolts and nuts and bearings, and you can find a complete list of all components needed for this project on the website article. Of course, you can also find and download the 3D model as well as the STL files needed for 3D printing. The link is in the video description. For 3D printing the parts I used my old Creality CR10 as well as the new CR10 version 3 3D printer. If you want to print the wheels in flexible material, you will definitely need a printer with direct extruder, just like the CR10 version 3 is. Both of these 3D printers provide great printing quality while being relatively affordable. So if you are interested, there is also a link to them in the description so you can check them out. When 3D printing the parts, it's important to use the horizontal expansion feature in your slicing software. I used a value of -0.1 mm. This feature compensates the expansion of the filament when printing. If not used, for example if the part has a hole with diameter of 20 mm, the hole of the actual 3D printed part will be around 19.8 mm and we won't be able to assemble it. Nevertheless, here are all of the 3D printed parts. To be honest, it's a bit crazy how much printing there is, but it's the only way we can get the unique appearance of the rover. Though you can cut the printing time in half if you choose to print only the functional parts of this rover. Alright, now we can start assembling the rover. First we need to prepare the aluminum profiles. I used a metal handsaw to cut them to size. We need 10 T-slot profiles for the base and 8 round profiles for the Rocker-Bogie suspension. For assembling the T-slot profiles frame we are using a suitable T-slot corner brackets and some bolts and nuts. Once we have the top and the bottom frames ready, we can complete the base by inserting the rocker joint 3D printed parts on the sides and some 3D printed brackets on the front and the back. For securing them in place we need M3 bolts and T-slot nuts. For the rocker joints I used M5 bolts and nuts. The distance from the front profile to the rocker joint needs to be 134 mm. Next we can insert the main bearing for the Rocker-Bogie suspension in place. Then we have the rocker joint shaft which will be attached to the base using an M8 bolt. The shaft has a slot where we can insert an M8 nut which is used for securing it to the base. The hole of the shaft is 7.5 mm so that we have a tight connection between the bolt and the shaft. In this way we actually reinforce the 3D printed shaft, as the bolt itself will carry some of the weight of the rover. This is the most stressed part of the whole assembly, as the whole weight of the rover is supported with this rocker shaft. However, the way we print the parts plays a significant role for their strength. I initially printed this shaft the easier way, where no support material is needed, but the print failed. In this way the main stress force acts on the layers which are not that strong, but if we print the part sideways, where the stress force will act on the wall contours, the part will be way stronger and won't fail. Nevertheless, now we will continue with assembling the Rocker-Bogie suspension together with the wheel joints and the motor mounts, and later we will attach these sub-assemblies to the rocker shafts. The holes of the parts where the 20mm round profiles go are dimensioned to have a tight fit, so in some cases we need to use a rasp or sanding paper to make them fit. Now for properly assembling these parts we need to make holes in the round profiles at precise locations. For that purpose, first we will mark a straight line on the profile. Next we can insert the profile into the 3D printed part with the marking line passing through the hole of the part. Then we can mark the locations where we need to drill the profile on both sides of the part. On the opposite side of the profile we need to repeat the same procedure. I drilled the holes using a 2.5mm drill, and then using a M3 bolt I made a thread in the profile which we will use for tightening the parts. The aluminum profile is softer than the bolt, so it's easy to make the thread with the bolt itself. Following this method for drilling the holes is very important, so that at the end all of the parts are positioned as they should be relative to each other. For the bogie joint we are also using 2 bearings and an M8 bolt. Once we complete the Rocker-Bogie suspension arrangement, we can continue with assembling the steering wheel joints. The steering wheel joint part is composed of two parts bolted together. For the actual joint or the connection between the servo mount part and the DC motor mount part, we use two bearings and an M6 bolt. At the top side or the head of the bolt we need to attach a servo horn, and we do that with the help of this 3D printed coupler and some M3 bolts. The coupler has a hexagonal slot through which the servo motion will be transferred to the bolt. At the bottom side we can screw the other part of the joint. We secure this connection with an M6 nut. This completes the steering wheel joint, although later on I will realize that we actually need to add another M6 nut at the bottom and tie it to the other nut. We need this because the motion of the servo is transferred to the DC motor mount part using the nut itself, and if not tightened with another nut, the whole joint will unscrew. The same procedure goes for the other corner joint. We know we have connected everything properly if we place this assembly on a flat surface and all three motor mounts lay flat or all of them are parallel to each other. Of course, we are using the same method for assembling the other side. However, we can note here that although some of the parts look identical, they are not the same parts, but they are actually mirrored. Next, we need to insert these sub-assemblies onto the rocker joint shafts on the base frame or the chassis. Before we do that though, we need to insert some threaded brass inserts in the shaft. Using a soldering iron, we can easily insert them in place, and so we get a good and reliable threaded holes for securing the suspension sub-assembly. We use 4 M4 bolts for that purpose. Once we install them on both sides, we can notice that the chassis falls or rotates freely. So we are actually missing something in order the Rocker-Bogie suspension to work properly, and that's the differential. With the differential, the two rockers are connected to each other and the Rover chassis. With this configuration, when one side rotates, the other rotates in the opposite direction, thus providing approximately equal wheel contact. The chassis will have an average pitch angle of both rockers. Here are all of the parts needed for assembling the differential. As the differential bar is quite long, I made it out of 3 pieces bolted together so that we are able to 3D print them even on smaller 3D printers. The differential bar will pivot in the middle of the chassis with a joint made of 2 bearings and an M8 bolt. For connecting the differential with the rockers, we need a rod end ball joint. I am using M8 rod end bolt joint, and we also need an M8 threaded rod with 50 mm length. The threaded rod goes into the 3D printed part, which has an M8 nut on one side, and on the other side it goes into the rod end bolt joint. Here we need to adjust the distance between the 3D printed differential link and the rod end, which needs to be around 20 mm in order the chassis to stay horizontal. For connecting the differential link to the rocker lever, we are using 2 bearings and an M5 bolt. We repeat this procedure for the other side as well, and with this our Rocker-Bogie suspension is completed. When one side goes up, the other side goes down and vice versa. This provides all wheels to be in contact with the ground all the time. The chassis goes only half the motion of the leg, or the chassis has an average pitch angle of both rockers. Okay, so next we can move on with installing the DC motors. The motors that are used are 37 mm in diameter, operating at 12 volts and have a gearbox with output of 50 RPM. However, I later realized that 50 RPM is a bit too much for this rover, so I would suggest choosing 20 or 10 RPM versions. For attaching the wheels to the motors, I made these shaft couplers. Here we need to install M3 threaded inserts, which will be used for securing the coupler to the shaft, and also M4 nuts for securing the wheels to the coupler. When inserting the nuts, we should also add some glue so they stay in place firmly, or use threaded inserts instead. Next we can attach the wheels. The wheels are composed of 2 parts. One is the wheel, which is printed in flexible material, but it doesn't have to be, and the other is the rim printed with normal PLA. The rim has slots which fit into the wheel, and so the power from the motor is transferred to the wheel. Here we can add few drops of glue at the slots to have them more secured. Finally, we can attach the wheels to the shaft couplers or the DC motors using 4 M4 bolts. Next, we can install the steering servo motors. I'm using high torque digital servos with 25 kg/cm torque and operating voltage from 4.8 to 6.8 volts. For securing the servos in place, we use 4 M4 bolts which go in the M3 threaded inserts in the servo mount 3D printed part. Alright, so next we can assemble the camera's unit. For panning the camera, I decided to use NEMA 17 stepper motor, but you can also use any other type of motor here. The motor motion is transferred to the upper section using a M5 threaded rod, which is connected to the motor with a 3D printed shaft coupler, and on the other side we use a bearing and 2 nuts for securing the threaded rod. For tilting the camera, I am using a servo which is the same as the one we use for the steering wheels. Many of the parts here on the camera unit are actually not functional and they are present just to match the appearance of the real rover. For assembling these parts we need various M3 bolts and some threaded inserts. However, I will also install a real FPV camera here. I made a custom holder for it so I can mount it on the housing of the camera unit. The camera is easily accessible from the top, which we can close it with a snap fit cover. Here's the final appearance of the camera unit. I mounted this whole camera sub-assembly in the front right corner of the chassis. At this point we can continue either with assembling the rest of the 3D printed parts, which are actually not functional but only to match the appearance of the real rover, or connect the electronics components and get the rover working. I decided to assemble all 3D printed parts first and then do the electronics. Just like I said, the following parts are just for matching the appearance of the rover, so I won't go in details how I assembled them. You can see how everything needs to be connected from the 3D model. I actually put a lot of effort designing these parts, paying attention to details in order everything to look good. These parts are also quite big and take some time to 3D print them. The last 2 panels in the middle of the rover are designed to snap fit in the rover. They will actually act as a hood which can be easily removed as the electronics components will be located in this area. The electronic components holder is made out of 2 3D printed parts bolted together and it goes to the bottom frame of the chassis. Alright, so now we can continue with the electronics. First we need to measure how much wire we need for each motor. I soldered the wires directly on the motors as I didn't have proper motor connections. I used heat shrink tubing for isolating the connectors. With the help of some zip ties we can guide and keep clean the wires. For the servo motors we can use servo extension wires to extend the wires to the electronics compartment. The electronics mount part has holes through which we can pass the wires to the middle of the rover. Overall, I think the wiring came out quite clean, with the wires passing behind the visible parts. Let's take a look at the circuit diagram of this rover now and see how everything needs to be connected. For driving the 6 DC motors, we are using 6 DRV8871 DC motor drivers, which support PWM control and up to 3.6 amps of peak current. The DC motor's operating voltage is 12 volts, with rated current of 1 amp and stall current of 3 amps. For powering the rover I am using 3S LiPo battery, which provides around 12 volts. The servos on the other hand need from 4.8 to 6.8 volts, so therefore we need to use a DC to DC converter, which will convert the 12 volts to 6 volts. The converter needs to be able to handle around 8 amps of current, as the servos that we are using are quite powerful and have a stall current of around 2 amps. For driving the camera unit stepper motor, we can use an A4988 or DRV8825 stepper driver. Using 2 resistors, we can make a simple voltage divider through which we can monitor the battery voltage. The RC receiver is powered with 6 volts coming from the buck converter, and the FPV camera in its video transmitter are powered with 12 volts from the battery. In order to keep the electronics components organized, I designed a custom PCB for this rover. The PCB will actually act as an Arduino Mega shield, as we will be able to directly connect it on top of the Arduino Mega board. In addition to the motor drivers, I also included a 3.3 volts voltage regulator and a dedicated NRF24L1 connection in case we want to control the rover using that module, as well as many other connections which can be used for attaching various sensors and modules. Actually, I tried to future-proof this PCB for upgrading the rover's functionalities. I ordered the PCB from PCBWay. Here we can simply upload the Gerber file, choose the properties for our PCB and order it at a reasonable price. I didn't change any of the default properties except for the PCB color, which I chose to be blue in order to match with the Arduino board. You can find and download the Gerber file on the website article or from the PCBWay project sharing community, through which you can also directly order this PCB. After several days, the PCB arrived. The quality of the PCB is great and everything is exactly the same as in the design. Assembling the PCB is pretty straightforward as everything is labeled. I started with soldering the pin headers at the bottom of the PCB for the Arduino Mega connection and then continued with the top side. I actually used pin headers for all connections because it gives flexibility to make changes if something doesn't work properly. I didn't solder the 3.3 volts voltage regulator as well as some other free Arduino pins as I wasn't going to use them now anyway. Once I finished with the PCB assembly, I secured the Arduino board to the electronics mount part using 2 bolts and then added the PCB to it. Then I connected each motor to their drivers and put them in place in the PCB. The servos go in their appropriate servo pins, as well as the stepper driver, for which I used one jumper for selecting a stepping resolution. For the radio communication, I am using the FlySky RC transmitter and receiver, which are really affordable and work great. For connecting the receiver to the Arduino, we can use servo extension cables as we need 3 wires, VCC ground and a signal pin. The receiver communicates with the Arduino through an iBus and a serial port. If you want to send data back from the receiver to the transmitter, in our case for monitoring the battery voltage, we also need to connect the sensor iBus of the receiver to another Arduino serial port. The buck converter is secured in place using 2 bolts, and for securing the LiPo battery, I am using 2 rubber bands, so in that way I can easily remove the battery for charging. The power switch goes on the back right panel of the rover. Make sure you double check your connections with these wires, because if you connect something wrong, you might fire up things. Lastly, we can connect the FPV camera to a 12 volts power supply and connect the video signal wire to the video transmitter, which also needs to be powered with 12 volts. With this, we are done with the electronics. We can put back the cover panels in place and we are done with this project. Actually, we are almost done, as we need to give life to this rover now or program the Arduino. Here we will take a quick look at the code, and on the website article you will be able to find more details on how it works. So using the iBus BM library, we read the incoming data from the RC transmitter. Then we convert these values into turning radius to right value, turning radius to left value, and rover speed from 0 to 100%. We use the turning radius R value for calculating the steering wheel's angle as well as the speed of the wheels. As I mentioned earlier, we are using the Ackermann steering geometry for calculating them. These values are then used for controlling the servos using the servo easing library, which provides smoother servo movements, and for controlling the DC motors using the analog bright function, which actually sends PWM signal to the DC motor drivers. Overall, the code is not that complicated, as the rover itself doesn't have complicated functions. However, I do plan in future videos to add more functions to this rover, like GPS navigation, various sensors, robotic arm, soil collecting mechanism, and so on. Nevertheless, that's all for this video. I hope you enjoyed it and learned something new. If you have any question, you can ask them in the comment section here or on the website article. Don't forget to subscribe, and for more tutorials and projects, visit howtomechatronics.com.